We're gonna be memed. We're gonna be memed. So, somewhere in this pattern of heads and tails lives what? What is in here that we were speaking of earlier? There's somewhere in there, yes? I asked a simple question over here. I asked, what's the chance you get heads? I want to introduce you to some notation today because I think that makes life easier. When we say, what's the chance you get heads, you can put a P for probability. And this is going to look like function notation from algebra. It's not. It's just a simple shorthand. So P for probability of. And then in the parentheses, you just simply put the event or the experiment you're talking about. So the probability of getting heads, or see, and that's the thing. There's not one unique way of writing it, Benji, because it's conversation.
T and H.
Exactly. So just getting heads on a coin flip. So I know you can, because I'm not loud. So the reason we like this is just because it breaks down the writing that we have to do, and it gives us a notation. So when you see it, just realize that this P just stands for probability. Let's use a different color. This blue is red is awesome up there. So this P stands for a probability. And then what you put in the parentheses is the event you're talking about. And when I say event of interest. We'll come back to that. I got some formal definitions that I think will help us kind of colloquially converse about this as we go through today and Wednesday. We'll come back to that. So we know, at least we kind of ballpark know what the answer to this question is, yes? What did we say it was? What's the chance of getting heads on a coin flip? We said it was 1 and 2. We said it was 50-50. We said it was 50%. I said it was 50%. I thought somebody had said that. Where is that here? I mean, you know what I see? You know what my eyes are drawn to? That. Isn't that rad? Who did that? The tails. Heads. Is that you, Jordan?
Yeah.
Isn't that phenomenal?
There's a heads chain. There's a
Oh, look at this! That's almost the exact, that is the exact opposite of Jordan's. If you look at that little chain right there, that's exactly the opposite of Jordan's up. That's what my eyes are drawn to. And the reason, and good, but you see the head chain over here, is there a corresponding tails chain somewhere? It doesn't have to be a chain, FYI, we'll come back to that. I bring that up only because that's what I look at now to check for randomness. I used to do a problem, it's too well known now so I can't do it anymore, where I tell half the students in the class to write down 200 H's and T's as if they were flipping a coin, and I tell the other half to actually flip the coin 200 times. And then I can mind read then. I can look at the results and say, oh, you faked. Oh, you're real. Oh, you faked. You faked. Oh, you're real. And I'm like, how the hell did you do that? And I just look for those runs. Nobody thinks to put runs like that in when they're trying to fake a coin. We're not random enough. As human beings, we're not random enough. We need patterns. Does that make sense? But the problem is, people have you heard about that before? How math professors can read minds by doing, maybe I should have done it. Yeah, I'll do it next time. But I read that in a book years ago, and I'm like, that's genius. Somebody showed me 2 coin flips of 200, and they said, spot the fake. And being a math geek, I looked at the top, and I said, that's fake, because it never has more than 3 in a row. It looks like this the entire time. Tails, heads, tails, heads, 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 tails, tails, heads, 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 tails, heads, 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 tails, tails. And it's never more than 3 heads or tails in a row. What was missing from the fake is anything like this. 1, 2, 3, 4, 5, 6, 7, 8, 9 heads in a row, or 9 tails in a row, or 10 tails in a row. Check this out. The chance, if you flip a coin this many times, the chance of seeing a strand like that of 6 or more heads or tails, what do you think the chance is? If you had to put a decimal on it. 96%. There's a 96% chance if you flip a coin 200 times. Like, this is about 200, probably even more. But if you flip a coin 200 times, there's a 96% chance that you'll see a string of more than 6 heads or tails somewhere in it. Just like Jordan saw. I think you misunderstood what I was saying. Jordan, you gave me the other answer. What's the chance of not seeing it? Slim to none. Slim to none. Because it has to happen because of the clumping of the randomness. We'll come back to how that does. So now that makes it seem even worse. Where's the 1/2? Where's the one at Micah?
Is it the overall?
There's 2 ways you can look at it. One way is that. Beautiful. Let's count, shall we? First of all, how many of you are in the room? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 16, 18, 19, 20, 22, 23. There's 23 of us, so we have 230. I counted myself. I did count myself. There are 230 of us in the room. So we have 2 votes for this right now. The first vote is it should be 1/2. The first vote is that it should be 1/2. We'll come back to that. I'm going to call that a theoretical probability because we answered that before we even were finished doing all this experiment. Now we're going to have what I like to call the empirical probability, which is out of the 230 trials that we did. And I want to see if these things come in pretty close to equal. So did you see what Micah said? I said, where's the half? He said, well, look at the entire thing and figure out how many heads and tails we got. Let's count the heads. Do it with me.
1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20.
20. Well, I'm going to keep track. I'm going to keep track. 20 heads. I'm going to keep track over here. Okay, go.
1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16.
Anybody keep track of how long each one is? Assuming we did it 230 times, it should be about 40, yes? This is pretty crazy. Go, go, go!
1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 12, 13, 14, 15, 16, 17, 18, 19.
We're going to go faster.
1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20.
Faster.
1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17. Yes.
Where the ADD comes in handy. Let's go.
1, 2, 3, 4, 5, 6.
All right. Sum them up. Now, first of all, predict. If it was perfectly 1/2, how many should we have? 115, yes? If it was perfectly 1/2, we should have 115. Let's see what we got.
3, 3, 9, 4, 5.
We're off by 10. By 10 out of 230. That is a half of 1%, yes? Being off. Less than half of 1%. That's impressive. We're off by less than half of 1%. So what I'm going to do is I'm going to do this. I'm going to put squiggly equals. We know it should be perfectly 1/2. Perfectly 1/2. We got 105 out of 230. And Nick's already said it's 0.495. So what you ended up getting?
I got 0.456.
0.456. 105 out of 230.
Yeah.
There we go. So you're talking about being off. You're off a minuscule amount. How can we make our estimate better? More runs. Increase the number of runs. Now I'll do that momentarily with Excel because it gets tedious to write on the board over and over and over again. It does. It gets tedious. But we can use Excel to simulate this, and I think I have a good visual to show it. So Micah, I love what you just brought up because you just described, I think, the most powerful way of dealing with probability that there is. I'm going to swing over here and talk about it.